So the limit rules go like this. If limit n goes to infinity an and limit n goes to infinity bn exists. By existing, I mean a finite number. You know, something like this limit is 3 and that limit is 4. Right? So I'm not, as opposed to say this limit is infinity. That's not the case. So I'm talking about finite number. Right? So if this exists, C is let me use a different notation. Perhaps I don't want to use C. I use a different notation. May I use K? And K is in R. Okay. Then you have several rules. So I use slightly different notation here than in the book. Doesn't matter. Then I can build other sequence, say an plus bn, and that automatically has a limits. And what is that limit? Whatever the limit of an is, and whatever limits of bn is, I just add them together. Is that convincing? Okay. Likewise, limit n goes to infinity, an minus bn is equal to limit n goes to infinity. Oh, sorry, I typo here. This I mean infinity. This I mean infinity here. Likewise, this is infinity. An minus limit n goes to infinity bn. Okay? Limit. So you have product, you have difference, and you have limits. I have that k sitting there. N goes to infinity. Suppose I build a very simple sequence, K-A-N, right? Then what do you think? This also has a limit. Must be what? K times the limit of A sequence. And I run out of space here. So next one I'm going to put over here. Likewise, limit n goes to infinity. If I build an times bn, a new sequence, then that one also has a limit. And you guess what? That should be limits of an times what? Limit of bn. Isn't that convincing, right? And likewise, limits n goes to infinity. If I build an over bn, then what do you expect? Limit n to infinity of an over limit n to infinity over bn. Provided, what I'm going to write? Provided what? Limits of n to infinity. This number, I know that this converges, right? So this limit is a finite, is an honest number. And that number is not 0. For example, if it is 3, then you actually have to worry whether this actually makes sense or not. Is that right? As a matter of fact, it could happen that you have finite initially, finite number of terms where bn is actually 0, then you cannot even talk about this quotient. Right? Correct? And so even if the limit of bn is not equal to 0, strictly speaking, some of the terms an minus bn may not even make sense, but it's okay. It's just finite number of terms of it. So long as this limit is not 0, for example, the limit of bn is 3, then once you get past a certain term, bn is very close to 3, and therefore definitely between say 3.1 and 2.9, then definitely it's away from 0, and definitely an over bn will make sense. So once you get past point, there's no issue of this quotient. And more than that, as you progresses, that quotient will be approaching very closely, the quotient of these two limits. So this should be convincing. All right. Finally, limits n goes to infinity. If you have an and you raise to a certain power, let's call it the book called it what? P. P probably is a good choice because it stands for power. And this law this rule actually can be considered as a special case of a more general rule, which I'm going to introduce. All right. So, but anyway, for now, it's just P is just a number, is a power, and this one you bet it is equal to 1. This one raised to P's power. If P is greater than 0 and limits n and an is greater than 0. And the reason for that is that if you have a negative number, over here, and an is negative, and you raise this to say -2 to the root 2 power, what does that mean?
Imaginary.
Yeah, that's is an imaginary number involved. It's kind of troublesome. All right, so we don't talk about it here, and therefore we try to avoid it. So everything is positive. Okay. All right. So and as I said, this is actually can be considered as a special case of a more general rule. So these should be, how to apply this, it should be, let me give you an example. Let's say a very commonly seen class of sequence would be a sequence like this. It's a quotient, the numerator and denominator are both polynomials in n. For example, 3n squared plus 2n plus 1. 4n squared plus 5n plus 7. What's the limit of an?
304.
304, right? 304. And we review a little bit of a power counting earlier this semester. You look at this, you notice that both numerator and denominator are polynomial in n. So as n grows, both are growing. And then you examine the power. It so happens that this is degree 2, this is degree 2. So in such case, the quotient converges to something. Okay? And in other words, intuitively, these two terms are insignificant in comparison with the leading term. And so if you block out these two, it's like 3n squared over 4n squared. N squared cancel out, you get what? 3 over 4. So that's sort of an intuitive understanding of it. How do you polish up? If you want to polish up, then an therefore is equal to, if you divide top and bottom both by n over n squared, the first term becomes 3, second term becomes 2 over n, third term becomes 1 over n squared. Likewise, numerator divided by n squared, 4 plus 5 over n plus 7 over n squared. Okay? Then, on the side, you prove the limits of certain simple sequences. For example, 1 over n, you prove that the limit is what? 0. And therefore, you see that if I start with 2 over n, that approaches 0. And then likewise, on the side, you also prove some very useful, very commonly seen simple example, 1 over n squared. You carefully use epsilon n proof, and then prove that it approaches 0, which after all is convincing, right? And then I use the first rule, then I know that this is going to be a sequence that also converges. Converges what? 0 plus 0, 0. And then I throw in another one, plus a constant sequence, 3. Which of course converges to 3, right? And therefore, the new sequence converges to 3 plus 0 plus 0, which is 3. Then at the same time, you examine this sequence 4 plus 5 over n plus 7 over n squared. That once again converges to what? 4. So you have this sequence converging to 3, this converging to 4. What is the next step? Well, ultimately you are talking about quotient of these two series. And then you use which rule? The quotient rule, where you see that this converges to 3, this converges to 4, 4 is not equal to 0, and therefore the quotient sequence converges to 3 over 4. Okay, so that's just a typical use of this. And I'll leave that to you. This, you should have already enough experience from last semester, and and so this kind of problem I don't expect it to be difficult for you. Right? So, but then I want to focus on two rules, which somehow have to do with the function f. Okay. Here's the extra theorem. If f is a function